Okay, yeah, so thank you everyone for coming today. It's my pleasure to introduce Dr. Cleo Loy, who is, for the moment, a postdoc in the Department of Applied Mathematics and Theoretical Physics at Cambridge. Cleo did her PhD at DAMPS and has done an incredible amount of work quantifying the effects of magnetic fields on oscillations in magnetized stars, specifically red giants.
I'm a client of
so Cleo, why don't you
and would like
go ahead.
You need to move Dick.
I think Dick muted.
Sorry, I've just muted everyone. Cleo, feel free to take it away whenever you're
cool. Yeah, thanks. And thank you very much for inviting me to give this presentation. So I'll be presenting some of the work that I've done doing my fellowship at Churchill College, or funded by Churchill College and based at DAMTP in Cambridge, that deals with the effects or investigates the effects of rotation and magnetism on the seismic properties of evolved stars. So there's been quite a lot of work done on rotation by others, but not that much work done on magnetism, and even less done on that combination. So this work tries to address some of those gaps. Right, so yeah, I mentioned Asteroseismology in my talk title. So what this is the technique of inferring the stellar properties by analyzing the oscillation modes of stars. And to do that, of course, what you need is a good framework for understanding how the mechanical properties of a star translate to its oscillation properties. So how this is done, I mean, this is possible observationally to detect oscillations, and that relies on the existence of fluid waves that can be excited through various means. So you have stochastic convection, you can also have stellar flares or global instability as they excite them. There are various classes of modes that can be supported, and depends on the restoring force, the main restoring force for the waves that constructively interfere to give rise to the modes. So for example, you have P modes that are formed from acoustic waves restored by pressure, and those tend to be localized to the surface regions. So this is the spatial amplitude function of a P mode. The red and black are the radial and horizontal components of the fluid displacement. And you also have these G modes that are restored by gravity waves, that are formed from gravity waves that are restored by buoyancy, and they tend to be localized to the interior, the core region. So how we actually observe these is due to the compression and rarefaction of gas in the surface layers. The surface temperature changes because the black body emissivity changes. Or the intensity changes, and this produces periodic brightness fluctuations. So if you take the power spectrum of a light curve, then what you get are a series of peaks corresponding to each mode. This is an example of one for the sun. So, and then it's a task of observing these frequencies and then using that to extract information about the properties of whatever you're looking at. So Asteroseismology has been quite successful with red giants, and there are several reasons for this. Firstly, red giants are quite luminous, so the signal to noise is quite good. You also have quite large radii, so long oscillation periods, small dynamical frequencies that mean that the signal is less likely to be aliased at typical instrumental cadences, so sampling cadences. And so, yeah, so this technique has been pulled from many stars other than the sun, most of them being red giants. Another cool thing about red giants, which makes them particularly successful for asteroseismology, is the existence of what are called mixed modes, which have properties of both the P and G like oscillations that I showed on the previous slide. So these have both large surface displacements, which make them easily observable because that induces a larger amplitude of temperature perturbations, and they also have appreciable amplitudes in the deep interior, so they're sensitive to properties. So the oscillation frequencies basically are more sensitive to properties right at the core. So there's been plenty of breakthroughs regarding red giant properties, so detection or measurements of core rotation, for example, detection of helium burning, which produces convection, therefore changes the buoyancy frequency profile. And there's also been some work that's investigating the possibility of using it to detect strong magnetic fields. So I guess just to clarify for this particular talk, the results I'm going to be showing deal with weak fields, which are in a different regime, or rather the signatures, the seismic signatures of weak fields are believed to be different from those of strong fields. And in more detail, I'm dealing with changes in frequency that are produced rather than talking about changes in the amplitude, which is more of this other work here. But that's for those who are more familiar with it and might have been wondering. So yeah. Right, so yeah, I guess before I dive into the details of the content of this research, I'll just give one slide general slide about stellar magnetism. So I did mention that it's been looked at less than rotation, but that's not because it's less important to, I guess, stellar physics, stellar evolution. It's more because it's harder to treat. But anyway, so magnetism in stars is believed to be generated actively by dynamos in regions that are convective. What regions of stars are convective depends on its mass and their evolutionary stage. So for example, on the main sequence, stars that are greater than about like 1.5 solar masses have convective cores. In stars of all masses during the protostellar phase, they're convective and throughout. And so you might get magnetic fields that are generated at that stage and then left over in subsequent stages of evolution. So, and magnetic fields are thought to be required to explain quite a number of phenomena, for example, angular momentum transport, chemical mixing. So for indirect reasons, it's believed that they need to exist. But as for how to directly prove that or directly observe them, these fields in the deep core of a star, that's quite difficult. I mean, it's not like surface magnetism where you can rely on techniques like spectropolarimetry. For fields in deep interior, I mean, what we have is pretty much numerical simulations and perhaps asteroseismology at your disposal. So there are lots of things we don't know. Existence, I mean, you've got plenty of arguments that say they should exist. But I mean, what kind of distributions of that? I mean, do they exist in all stars? Do they exist? And what's the strength distribution? I mean, do some stars have very, very weak fields or moderate or strong fields? That's not really known, not well constrained at least. What the configurations are like is almost complete mystery. I mean, you have some simulations of main sequence dynamos that, I mean, suggest some sort of structures, and there's lots of variation. And then what happens when dynamo shuts down the star, the magnetic field settles into some kind of equilibrium. There's also uncertainties there, and also how it changes over the lifetime of the star. And so I've got this image here of this butterfly diagram from sunspots. I mean, the most well-studied, I guess, stellar magnetic field is that of the sun, and we know that's complicated. It changes in obliquity over the solar cycle, also changes polarity, and it follows it's got all these periodicities that we can sort of maybe only partially explain, but very dynamic, very complicated. So the goals of this work are to perform a phenomenological study of rotation and magnetism in evolved stars and see how those affect the seismic properties. Now, there are a number of assumptions that are quite central here, which I'll now list. So firstly, we assume that both rotation and magnetism are weak, in the sense that we can use perturbation theory to treat them. Now, in the case of rotations, it's observationally kind of established that you can, it's slow enough that you can use perturbation theory. For magnetism, I mean, we have no idea really, but I guess I'm just saying that I'm restricting myself to the regime where we can use perturbation theory, so where it is weak. They are assumed to be of comparable strength as well, but both weak. Both rotation and magnetism are assumed by themselves to be axisymmetric, and rotation is assumed to be solid body. Now, I mean, differential rotation is a thing that is established, but in regions that are magnetized, there are arguments that the magnetism should induce solid body rotation. So that's just, I guess these are sort of the simplest realistic, configurations or backgrounds that we have. Yeah, so the more novel aspects of the work are that we are going to allow rotation and magnetism to be misaligned. So I said they're axisymmetric, that's with respect to their own kind of native axis, but they can be inclined with respect to one another. So we have this obliquity angle beta. And another thing that we're going to look at is the influence of the field topology. Now, this is kind of motivated by this knowledge, at least on my part. I was kind of curious about this because the most well-studied dynamos, which are those of the sun and the earth, they exhibit periodic flipping. So for example, on the earth, you have this evidence for it in the magnetization patterns and seafloor spreading. And also on the sun, like with the sunspot diagram I showed in the previous slide. And also actually in some simulations of main sequence dynamos in massive stars, there's some evidence that you may get the same kind of flipping. And so what happens, I guess, is as the convective core retreats on the main sequence or recedes in the main sequence, you might leave behind kind of shells of alternating signs. So you leave behind this fine scale radial structure. And the effect of that on the seismic properties, I thought was something that might be interesting to have a closer look at. So the things that I'm going to have a look at the radial extent and radial scale, so this flipping scale of the field. Right, so now I guess I'll spend a couple of slides talking about the theory behind the mechanical properties, how you treat the mechanical properties of the star, because that's central to the whole. How do you understand or interpret a seismic spectrum, what that means about the material properties. So I guess you have stars that are self-gravitating fluids. You might expect that they're governed by the usual equations of conservation of mass, momentum, and Poisson's equation for the gravitational potential, relating this to the mass density distribution. So for the momentum equation, on the right hand side, we've got these sum of the forces acting, and in a typical star, pressure and buoyancy are dominant. Coriolis and Lorentz forces are relatively small. So this is the motivation using perturbation theory. Essentially, you neglect Coriolis and Lorentz forces and solve the equations on the just pressure and buoyancy, and then calculate the correction associated with these two terms away from the initial solution. So the stars are basically spherical, and so to model a standing mode, we adopt this following ansatz for the fluid displacement vector. It separates out the spatial and temporal components. So this is the spatial amplitude function, and then each point in space is oscillating time harmonically with a certain frequency, omega. And we work in spherical polar coordinates, so r, theta, phi. Right, so neglect rotation and magnetism. The backgrounds are going to be spherically symmetric, and then it makes sense to expand in spherical harmonics. Now, you don't have to, you can expand in spherical harmonics even if the background is not spherically symmetric. It's just that if it were, then it becomes useful because each individual mode is associated with a single spherical harmonic, but otherwise you're going to get an admixture, and that's something we'll get to later. But anyway, so this, if you adopt this expansion where you have a summation over the spherical harmonics YLM, RL and HL are the spatial amplitude functions that are the black and red curves that I had earlier. And then you can substitute those into the equations in the previous slide, and you linearize, expand and linearize, make the Howling approximation, which assumes at the most small spatial scales. You boil everything down to this set of second order ODEs, or the pair of first order ODEs in the radial coordinate. And these are the equations of stellar oscillation. So these coefficients here are all background quantities that will depend on background quantities, with the exception of omega, which is your kind of the eigenvalue. So if you solve this pair of equations under appropriate boundary conditions, then this is your eigenvalue, your eigenfrequency that comes out associated with each solution. Well, L is a parameter that you choose. L is the spherical harmonic degree, so that's something else that you choose. Yeah, so, and note that these equations have no M dependence, no explicit M dependence. So what happens is when you take the inner product with a spherical harmonic YLM, the M dependence cancels out when in that projection step. So what that tells you is that well, you don't need to solve for or input any value of M. So there's a degeneracy with respect to all M values. And that, of course, gets lifted by rotation and magnetism, which are non-spherically symmetric backgrounds. So that brings us to, I guess, perturbation theory. So if the backgrounds are almost spherically symmetric, then you can treat this by calculating the correction to the frequencies from your initial unperturbed frequency. And I guess most people have seen this in some form or other, because it's like in quantum physics, for example, with the Stark effect and electric fields lifting the spherical symmetry. And I guess I'll be talking, I would like to go through this because the case where you've got two perturbing effects that are misaligned has been less widely seen, I suppose. And it's important to some of the quantities that I'm going to show later. So anyway, so let's start off with single perturbing forces. So let's say, for example, pure rotation. What you get is a lifting of the multiplet, which has in total 2l+1 kind of degenerate modes into this set of symmetrically split peaks. And this is the case of pure rotation. So this is, I mean, the example here is L = 2, so you've got 5. And to first order, they're evenly spaced by a value proportional to the rotation frequency big omega. Okay, so then for pure magnetism, what you have is that the modes of the same absolute value of m remain degenerate, but and so you get a splitting into L+1 peaks, in this case 3, and the shift from the unperturbed value is proportional to the square of the field strength. So that's what you get in just, single forces. But what about when you combine them? So if they're aligned, I guess you might suppose that this case is straightforward, right? You would say, well, we just add them together. So calculate the value for rotation and magnetism, and they just add. And that's fine. But what if they're oblique? So this is where it gets complicated, because the m value associated with the rotation axis is not the same as that associated with the magnetic axis. They're just different axes in space. So like m = -1 of rotation is completely not the same spherical harmonic as m = -1 of the other axis. So what you instead have to do is treat the problem as involving an admixture of m. And that's what we're going to get to. So, right, so this is the treatment that you have to kind of go through. So if you have oblique rotation and magnetism, you need to work in a co-rotating frame, because the modes naturally exist in a stationary frame, and that's the only frame that is stationary. If they are aligned, you can work in either co-rotating or inertial frames, but that's not the case in the oblique. So we have to work with the co-rotating frame frequency omega bar. And if you do that, then the equation of motion, well, you can write it in this form, and this is an operator form. L0 comprises the pressure and buoyancy terms, and then L rho and L mag are the Coriolis and magnetic terms. So you expand these quantities, the co-rotating frame frequency and fluid displacement vector as follows. So the subscript 0 refers to the unperturbed value, and you want to solve for the first order corrections to that induced by the presence of these two terms, which were in there before. So substitute into this equation and retain up to first order terms, and you get this. And so what you do next is to notice that psi naughts form a orthogonal basis, a complete orthogonal basis, and you can expand any psi1 in terms of that as a superposition of that. So we substitute that into this equation and you get this. Now the next step is you have to be careful. So if L1 is axis symmetric and there's got no phi dependence, then you can regard psi naught. So this equation is from the point of view of psi naught j, the jth eigenmode. Then this can be regarded as only being made up of a single m. So when you take the inner product with an appropriate spherical harmonic, all the other m's vanish. And then you get this. So the goal is to isolate omega 1 bar. It's the thing we're trying to solve for, and you get this. So I guess this is probably familiar from anyone who's done like undergraduate quantum physics, the standard results of first order perturbation theory. Now the complications arise if L1 is not axisymmetric, because then, so if this has a phi dependence that is not just e to the im phi, then taking it in a product with another spherical harmonic won't cancel out the other m's, because it won't give you your delta function, the delta of the difference between the m's. So then you have to regard these as being admixtures of multiple values of m. And that's what we're going to get to. So there are essentially two coordinate frames, one with respect to the rotation axis and one with respect to the magnetic axis that your spherical harmonics is defined. So you define these angular coordinates theta phi for the rotation axis, and then theta prime phi prime for the magnetic axis, and two sets of m and m prime that go along with that. So you expand your fluid displacement as a superposition of these different m, and am is the coefficient representing how much of each value of m is in there. The primes represent what coordinate frame you're in. And then so the only difference between these two coordinate frames is they're rotated by angle beta. So and the angular dependence of the fluid displacement is captured in spherical harmonics. So what we need is the transformation law between spherical harmonics in different frames. And that's given by what's called the Vignette D Matrix. So I've not got the expressions of these coefficients written, but they're the kind of thing you can just look up, and they're like a function, they involve trig functions and factorials, depending on this obliquity angle beta. And what that leads to is this transformation law between the coefficients a and a prime and the two different frames related by this matrix D. So that then gives us this slightly different expression for omega 1 that we're trying to solve for. So rather than that scalar equation that I had on the previous slide, we now have a 2L plus 1 by 2L plus 1 matrix equation. And these are m rod and m mag, and we are assuming that the rotation, rotational frequency field and the magnetic field are axisymmetric with respect to themselves. So these are diagonal matrices, but the mixing comes up because of this coordinate transformation that's specified by D. So you have to they couple everything together, and you have to solve for all 2L plus 1 modes simultaneously. So there are 2L plus 1 solutions to this equation. So gives you 2L plus 1 eigenvalues for A, and then 2L plus 1 eigenfrequencies or eigenvalues omega 1 bar. Now, if you were to then, so each of one of these solutions is in turn a superposition of 2L plus 1 values of M. So when you transform to the inertial frame and you Doppler shift each of these by M omega, what you actually end up with is 2L plus 1 squared frequencies. Now, most of these are not real modes because, well, there are only 2L plus 1, at most 2L plus 1 real modes. So many of these peaks that are going to appear in the inertial frame, like in observations, are fictitious modes, I guess, if you think about it that way. But yeah, so I've explained all this because I'm going to be showing the structure of A, your eigenvectors, and M rod and M mag in following slides. And it's kind of rather, maybe a lot to take in. But yeah, okay, so.
Cleo, I'm kind of confused here, so I can ask a question. So how many, there should be 12 plus 1 modes, but then you mentioned there's all these vector 12 plus 1 squared frequencies. So in which frame is it that we actually can easily count 12 plus 1 modes?
That's a co-rotating frame. So that's the frame in which the true modes reside, because that's the only stationary frame that actually exists.
But each M value has a different co-rotating frame.
Each M value? Oh, I meant co-rotating with respect to the surface of the star. So I'm not actually talking about respect to each spherical harmonic. It's just if you imagine you're standing on a star, and this is solid body rotation, then that is the frame that I mean by, that's what I mean by co-rotating.
Right, in the rotating frame, there are.
So in that frame, there are 2L plus 1 modes. So in that frame, an observer would see 2L plus 1 different frequencies. But it's once you come off your surface of the star, you look at it from an inertial frame observer's perspective, then you get this additional stuff happening. But the inertial frame is not a stationary frame, so you might not expect there to be that number of modes anyway.
Okay, thanks.
No worries.
Could I make an even simpler question? You've referred to things to the surface rotation, Are we able to deal with this expansion in terms of arbitrary differential rotation in the interior?
That's a question that I don't have an answer to. I don't quite know how it's going to work if your frame actually isn't stationary. Because what I understand is that perturbation theory can only apply if the background of the star and the frame where the background of the star is not changing. So my best guess in an analogy to what's happening here with the inertial frame is that you're going to get multiple fictitious modes in any frame, but I don't know how that is going to work in practice.
I imagine it's pretty complicated, actually.
It would be.
Yeah, but it's
perhaps,
probably a worthwhile thing to look into.
Yeah, but I mean, the fact is that if there is magnetism, then that's thought to enforce strict solid body rotation wherever it is. So that sort of resolves that problem, but I don't know what will happen if there was both. Well, there was no stationary frame.
Solid body rotation on magnetic surfaces, right? But if these were aligned, you could get differential rotation on different magnetic surfaces.
Yeah, in that case, if you had axisymmetric field, then you would have the only possibility is aligned rotation and magnetism.
There's no guarantee there's standing patterns in such a complicated system, is there?
Probably not. I mean, what you mean if it were misaligned and differentially rotating?
That's right. Is it a guarantee that by the time the wave comes back, propagates and comes back, it's going to close on its own?
So the other thing I'm thinking now is that, I mean, if there was differential rotation, then would additionally advect the magnetic field. So your magnetic field wouldn't even just be a stationary solution. So I really don't know what's going to, the differential rotation is going to drag around the field. I suppose you get a dynamo, don't you? And then, I mean, I suppose you might get propagating waves. They probably wouldn't constructively interfere. They would be damped somehow. Yeah, you might well not get nice normal modes anymore. Because that would be the situation, for example, the sun is in, at least the dynamo region of the sun is in. So you could get like evanescence perhaps in that region. I don't know, it'd be very complicated. Okay, so I guess I'll move on. Right, so these are the stellar models that I've used to do the calculation subsequently. So these are just generated using laser standard publicly available stellar evolutionary code. And they're generated without accounting for rotation and magnetism. So these are just the plain spherically symmetric profiles. So there's two models considered here. They're both evolved stars, evolved stellar models. One's a subgiant and the other is a red giant of the same mass. These are two solar masses. And these are the background profiles that we use to calculate the unperturbed modes. So that's profiles of pressure, density, well on the left, density, pressure, and then the buoyancy and LAM frequencies. So the black is the buoyancy frequency, and then the red, green, and blue are the LAM frequency for L equals 1, 2, and 3. The dashed line indicates where we choose to impose the magnetic field. So the magnetic field is assumed to lie within the central region. And also these are not actually shown up to the full stellar radii because that's quite large. These are just zoomed into the core so you can see the structure there. Great. So these are the modes that result from solving this pair of equations for those profiles. So in the middle panel here, we have the frequencies versus the radial order. These are negative because it's a convention in astroseismology to count G-like crossings negatively. So but roughly speaking, it's the number of nodal crossings of your spatial amplitude function. And the different colors are for different values of L. So red, green, blue are L equals 1, 2, 3. That's the color scheme that's used throughout here. This on the bottom left is an example of one of the eigenmodes for L equals 1 and equals minus. This is one of these ones, showing you what it looks like. So the black and red are RL and HL, and the inset is a zoom into the core, so you can see this very fine scale G-like oscillations occurring there. The frequency range that we solve for is between 8 to 12 times the dynamical frequency, which is the typical range for stochastically excited oscillations through convection. It's generally around like 10 plus or minus like 2 times dynamical frequency. On the right here, we have what I've shown is the mode inertia, which is given by this expression, and it's a measure of the amount of mass displaced by the mode. So it's a measure of the G-like character, because you got mass concentrate towards the center. So it's larger for modes that have larger amplitudes in the center, which are your G-dominated modes. These dips here occur where the modes are more P-dominant, and these are actually the ones that are most easily observable because they're associated with larger surface amplitudes. Anyway, yeah, so that's those. Okay, now so I'll now talk about the magnetic field configuration. So what I've used in this work are these twisted torus configurations, which on the basis of analytical and numerical studies are thought to be the kind of stable configuration that you might expect to occur in reality for magnetic equilibria. So this, for example, is a numerical study by Braithwaite and Nordland, where they've evolved random initial magnetic field configurations, and they evolve quickly and they settle into what looks like this twisted torus, twisted donut. And they find this to be quite ubiquitous. And then some earlier work by Prendergast actually finds a way to construct qualitatively similar fields analytically. And all you need are these two quantities, your radial flux function psi and the parameter lambda, which is a root of this equation. And because J1 is also, so J1 is the spherical Bessel function of the first kind, and this is oscillatory, so you can actually have multiple lambda roots, and what they correspond to are different topologies. And we'll see that later. This is actually how I parameterize different topologies, different radial structures. So yeah, and the magnetic field components are related to psi and lambda in this form. So once you have that, you just plug it in there and you get your components. And yeah, the primes here are because this is in the magnetic, with respect to the magnetic axis, I'm using these primes. So yeah, once you pick your value of, or solve this, pick your favorite value of lambda and then construct psi just using this expression. And yeah, and then plug that in. So this is, I guess I've been calling this a Prendergast solution after this work that first found it. J1 and Y1 are your spherical Bessel functions, the first, second kinds. The first kind. And this proportion, so the scaling of this is determined by however strong you want your field to be. But that is the shape, this sets the shape of your configuration. So what this actually looks like, I think this is subgiant, this is for the subgiant model. This is the first 6 roots of lambda for that model. So that's the lambda value is shown in the header. So what's shown, so these are all axisymmetric configurations. So what's shown is a meridional half plane where the axis of the field is on the left. The color represents the strength and direction of the toroidal component. So red is into the page, blue is out of the page. And then the black lines are the poloidal projections of the field lines. So you can see that as lambda increases, you get increasingly fine radial structure. And lambda actually quantitatively sets, roughly speaking, your inverse radial scale. So it's got units of inverse length. And yeah, so as kind of motivated by this idea that you might get such alternating shell structure if you had like a periodic flipping dynamo. So other parameters that you need in order to actually construct these fully are your field radius, i.e. the maximum radius beyond which the field vanishes, and then your amplitude, here controlled by the central field strength. So these are the parameters that were used for the 2 stellar models. The value of the field strength was chosen so that the magnetic shift would be of comparable value to the rotational shift that is known from observations. So the actual values of the field that corresponds to are shown here. So about 1 megagauss for the subgiant and about 0.4 for the red giant. And if you compare the dynamical speeds, it's much smaller. The alphane, central alphane speeds are much smaller than dynamical speeds. So you should still expect to be good for perturbation theory. The radius of the field is chosen to coincide with the mass coordinate of what would have been the boundary of the convective core when the star was on the main sequence. And that you can see that from the composition profiles, that I haven't shown those here. So as a function of the stellar radius at the ages, respective ages of the star, that's what they are. Right, okay, so here are some results. So this compares, so on the vertical axis of each of these 3 panels is the frequency shift, and that's versus the unperturbed frequency. The red, so this compares pure rotation, so without any fields, with what happens when you add a field. So black is pure rotation, and then the red and the blue are where you have magnetism of different obliquity. So red is magnetism that's aligned, and blue is inclined. So the 3 panels, I mean, these 2 are for the subgiant, and the right one is for the red giant. These are L equals 1 and 2, and the right one is just L equals 1. So what you see from just looking at these are that, so each multiplet is just going to be like the single value of omega naught, your 3 kind of dots of a certain color. And what we see is that the p-dominated modes, which are the ones that these dips, are more symmetric, meaning evenly spaced, compared to the G modes, which are the others. And I guess you can understand that from the fact that you've got, well, a core confined field, and magnetism induces, like magnetic fields induce asymmetry. So you would expect then that the G-dominated modes are less symmetric. This asymmetry is more pronounced at lower frequencies in general. And you can understand that because, and I didn't show the expression for this, but MMag, the magnetic kind of matrix, has an inverse frequency dependence, whereas the rotation matrix, M-rot, does not have an explicit, well, to first order, does not depend on frequency. So yeah, as a result, you have more magnetic effects being important at lower frequencies. I guess physically, you can also think of that as at lower frequencies, you have shorter wavelengths. And if you have shorter wavelengths, then the alphane frequency goes up. So you bring your alphane frequency is closer to your dynamical frequency. And so you might expect magnetic fields to become more dynamically important. Yeah, and one curiosity that I noted is that for L equals 1, for some reason, the beta equals 4 case, so the moderate obliquity case, you have the blue multiplets being more symmetric than the red. So this is the same field strength. It's just that if you change your obliquity, you can end up with a case that potentially might look quite symmetric across the entire frequency range. So it's just something to think about and watch out for. Like, you can't necessarily use the lack of asymmetry to rule out a field, because there are certain parameters, parameter combinations for which they might actually appear to be quite symmetric. But this doesn't occur for L equals 2 for whatever reason. I don't have a good explanation for this. It could be just like coincidence. Okay, so these are what the structures of MMag, MROT, and the A eigenvectors look like for 3 values of L. This is for a single mode, well, a single mode for each value of L. So that's the eigenvalue problem that we're trying to solve. A is, so when D is, so when beta is 0, D is the identity matrix, and this just reduces to a diagonal system. So then you get exactly the case of the, well, of the aligned case, where you just have a scalar equation for omega 1. So A is then just the identity matrix. But once you have non-zero beta, so the values of beta are shown in the headers here. So the left one is beta 0, and the right one is beta is pi3, some intermediate value of the obliquity. You start to introduce these off-diagonal components of A. And that gets progressively worse as L increases. So MROT and MMag, as I mentioned, they're diagonal because the magnetic field and the rotation field, I guess, are both axisymmetric. But anyway, you can see the values of these entries as you change L. And I guess so the explanation for why you get more of this mixing with increasing L is because MROT decreases with L, whilst MMag increases. There's actually explicit L dependence in MMag. I didn't show the expression for this. And MROT, you can, I mean, that's from from asymptotic theory, for example, for G modes, you have the rotational spacing being inversely proportional to L into L plus 1. So I guess that kind of explains that there. So, not doing very well for time. So now we'll have a look at what happens to single modes. So this is from the point of view of just one mode, and this is L equals 1. The 6 panels show different values of beta. So this essentially shows the splitting process. So that on the left, that one line is the unperturbed mode. The middle group are the frequencies. It's a frequency shift. It's a frequency shift in the co-rotating frame. And then on the rightmost group are what you might see in the inertial frame. So the saturation or the grayscale level of these lines corresponds to the absolute value of A. So this is kind of the amplitude of the mode that you might see in the inertial frame. And I guess there are two things that are kind of interesting from here. Firstly, it's possible for these to look quite symmetric, especially for intermediate values of beta. So it seems to just be a thing for L equals 1. I'm not entirely sure why, but yeah, again, it does mean that you can't use apparent symmetry to rule out the presence of a magnetic field, because the field strengths chosen here are such that mmag and mrot are comparable. So the magnetic shift, or the kind of magnetic contribution, is comparable to rotation. So it's quite a substantial field, as it were. The other thing to notice is that even though there are quite a large number of peaks or apparent peaks in the inertial frame, it's possible for only a small number of these, like 2L plus 1 of these, to actually have high amplitudes or to be dominant. So the thing is that if you had a spectrum that was noisy, then it's possible for a lot of these weaker peaks to be lost in the noise. So you can't alone use kind of the lack of multiplicity to rule out a field as well, especially if your spectrum is quite noisy. Okay, I might just hurry through the next one. So these are just for other values of L. You see greater kind of mixing here. And then this next one is for greater field strength. So I forgot to mention the dashed lines are the values of the modes the values of the frequencies in the case of pure rotation. So this is just comparing the value of the kind of spacing to what they would be if you didn't have a field. So you see that the multiple's shifted, but the spacing is quite similar. And I've not actually shown them here because the values are just too different to bother. But yeah, turn out the field strength is 2 times higher, much more of this kind of admixing of M. Okay, and this is a summary. I mean, in the interest of time, I'm probably not going to talk through exactly, there's a lot of dimensions being plotted here, but I'm not going to talk through what exactly the plots show. Can ask me later if you're interested. The conclusions from looking at this are that you have more M mixing at larger obliquities, which are the lower panels, and larger field strengths, which you've seen. The G-dominated multiplets tend to be shifted to higher values systematically, and well, this is because they are more affected by the magnetic field, and the magnetic shift is positive definite. So this discrepancy, I guess, is centroid offset between the P and G modes is larger at lower frequencies, and that's because the magnetic field is more important at lower frequencies. And we mentioned that was physically interpreted in terms of the smaller wavelength at smaller frequencies that associate with the larger alphane frequency, k.Va. So that's there. And next, let's look at the effect of field radius. So this is these 2 panels have 2 different models, stellar models. What's plotted on the vertical axis is just the magnetic shift. And this is going to be in the co-rotating frame. And that's versus the field radius. So we've now tried out some different values of RF. And the different colors are for different values of L. It's the same scheme as I've been using in other plots. And the different marker types are different values of M. So what we see, sort of roughly speaking, is that for whatever value of L or M, you get this increase in the magnetic shift with RF. And I suppose that's not too surprising because you've got a larger volume of field. So this is the same central alphane frequency. Same central alphane speed, by the way. There's kind of just more volume of field over which your integral is going to be larger if you integrate over a greater volume. So, but it's not quite straightforward. You do see these, variations, these fluctuations in the trend. And that tends to be broken up by this topology changes. So scaling up the field radius isn't quite a simple scaling of the whole configuration. That's the way in which the Prendergast solution is kind of set up, because depends. So one of the inputs is the density profile, and that does not scale with RF. So as a result, that kind of induces this non-monotonicity in the trend. So that was the view for just single modes. This is the view across the whole frequency range. And now we've added rotation. And yes, that's the value of rotation. And this is aligned just for simplicity. So yeah, same color scheme for different L values and marker styles for different N values. And what we see from here, I guess, just simply speaking, is that, well, for smaller omega, there's larger shift, also for higher L and more G-dominated modes. And we've all kind of reasoned all that before. And these are for two different values of RF, so differing roughly by a factor of 2. And the steepness of that slope, which is induced by the magnetic shift, is larger for larger RF. So again, in line with what we've already seen, that larger field radii produce larger magnetic effects. Next, for topology, we have, so this is, again, vertical axis shows the magnetic shift versus lambda, your inverse radial scale. And generally speaking, I mean, there's, again, some complications that relating to topology. This drop off, this decrease in the shift with increasing lambda. So decreasing radial scale in the configuration leads to smaller magnetic shifts. And this turns out to be related to the steeper radial drop off in the field strength. Now, this may well be a quirk of the Prendergast solution, because I am assuming a kind of just a certain, functional form here. But there is a physical argument for why you might get lower field strengths for fields of finer radial structure, and that's simply because of ohmic dissipation, because they would operate faster on smaller spatial scales. So, I mean, that's about as much as I can say, but that's what we see here. So again, this is now a look across different frequencies, and is very much the same deal. There's not too much more new stuff to be said here. But yeah, you see the same large magnetic shifts for smaller omega, higher L, more G-dominated, and these effects are more pronounced, or steepness is more pronounced when lambda is smaller. Right, so this is, I guess, kind of an important summary slide, because this talks about the implications of all these results for asteroseismology. So to say more about this, okay, so what you've seen about multiplet structure. So the Lorentz force is known to cause asymmetries, but one, I guess, taking point here is that just because you see a symmetric multiplet or have detected one doesn't mean there's no field, or a field that's not kind of comparable to rotation, because under certain sets of parameters that can happen. So yeah, so I guess the message is you need to kind of do kind of a thorough fitting and study in that regard. Another point is that we've seen that with this obliquity, an important consequence is the appearance of these fictitious, or this much greater additional multiplicity, but it's still possible for only 2R+1 peaks to dominate. So if you have noise in the spectrum, you may be, burying the multiplicity that might otherwise be there. So, okay, now with regards to the behavior of the magnetic shift, it's positive definite because mmag is positive definite, and so that's in contrast to mrot, the rotational matrix, which is not positive definite. So rotation won't shift the centroid frequency of the multiplet, at least not to first order, but magnetism will. So that's like as one signature to look out for, even under these sorts of complications with regards to the multiplet structure. So one thing to look out for that will always be true is this positive definite shift, if that can be detected. And it's also, and if you detect this, other things to look out for are that it is going to be larger for lower frequencies, larger L, more G-dominated modes. And I didn't really talk too much about this, but also for stars with higher central condensations, all else being equal. And the reason for this is that if the buoyancy frequency is higher, then for a given frequency, your spatial scale of your modes is smaller, and so your alpha frequency is higher. But yeah, so one kind of spin-off, I guess, of this work is the possibility for seismic inference of the field structure. It wasn't really a goal, but so I guess the idea of like trying to fit for a three-dimensional complicated vector field that you don't really know very much about. It just seems like an impossible problem. But actually, these Prendergast configurations, which are reasonably complex, I mean, they have, you know, some kind of structure, they are axisymmetric, for example. Like these Prendergast configurations are actually, to generate one of them, I just have to choose 4 numbers, and they are the obliquity, the central field strength, the alpha speed, the field radius, and lambda, that root of that equation. And that is all you need to generate a field configuration like this. So if you were to kind of believe that a Prendergast configuration is a realistic kind of thing in reality, then actually what like seems like might have been an impossible problem can actually be potentially tractable. But yeah, that does make certain assumptions about the structure of the field algebraically as well. But yeah, okay. So in summary, so yeah, we've had a look at this study of frequency splitting patterns induced by rotation magnetism. We used first order perturbation theory and applied this to Vol stars with core confined fields and looked at the influence of topology and obliquity. Yeah, take-home points are obliquity produces complicated effects. So to actually make conclusions about the existence of a magnetic field and to interpret any multiplet structure properly, you do need to do proper modeling. And that's, I think, yeah, something to take forward. So, yeah, and we've seen that the effects of topology are that finer radial scales produce smaller shifts, and also you get smaller shifts for smaller field volumes, which I guess are both kind of sensible things to say, but we've demonstrated that explicitly. And also, yeah, it may be that, you know, if you adopt Prendergast configurations as your go-to solution, then you really just are fitting for 4 numbers, for global kind of parameters. And that may end up being something that's tractable and perhaps should be looked at some point. So yeah, I'll end there. Thanks very much for listening.
Thank you very much, Cleo. Do we have any questions for our speaker? It's a fantastic talk. Thank you.
I guess I have a question.
Yeah, go ahead.
So I guess this is a technical question. Would you mind going back to your plots on the mode inertia?
Sorry, say that again.
Oh, sorry. You had a number of plots a while back, calculating the inertia of the different eigenmodes that you calculated in your work. So I guess my question is, what's going on with the frequency scaling with these mode inertia? With yeah, because so I'm familiar with G modes, and they it seems like the G mode frequency scalings are a little bit different. But you're also when I did these calculations, it was a different point in the stellar evolution. So what's going on, I guess, with the frequency scaling with the mode inertia?
What do you mean with the frequency scaling? Yeah. It's a linear axis.
Yeah. Sorry, I'm being really confusing.
That's
yeah.
the G dominated versus P dominated, right?
Oh, they're different. They're different modes. So the top are P modes and the bottom are G modes.
The bottom are P modes. So low mode inertias are P modes.
Okay. That makes sense.
Less mass.
Yeah. And then also, what is the cause of the really sharp dips in the inertia?
Well, in these plots, you've got many more G modes than P modes.
Okay.
So if you didn't have coupling, the G modes, I mean, they'll outnumber the P modes by a factor of, I don't know, several tens to hundreds. And so this mixing process, the sharpness of the dips depends on the strength of the coupling. So in the subgiant, you have more closely coupled cavities, and I guess it's a bit smoother, like you've got more modes in the intermediate values. But for the red giants, I think the cavities are less well coupled, and you have just sort of only if it's very close to the P frequency, the kind of pure P mode frequency, that you actually start doing anything funny to it. So that's the, I guess, qualitative reason for the sharpness.
Okay, thank you.
Can I ask a question about just the phenomenology? So brought up by this plot here. The P modes, these are giants or supergiants even. So they've got convective envelopes, and that'll excite P modes. So do you see the P modes, because they have a very low mode inertia? Or do you see both P and G modes? And if so, what's exciting the G modes?
So they're all mixed.
Primarily, yeah, no, they're all mixed, but yeah, the ones that look more like P modes.
So even the the ones that look more like P modes. Well, convection occurs in the envelope.
Right.
So that's why, well.
That's why you have a low inertia,
That's
but that's also where they're excited. So you might think if you've got a low inertia and you're excited there, you get a higher amplitude than you get from the G modes.
You probably do, yes, and they're also more observable. So
yes, okay. So in like Kepler or whatever, most of the modes that people see are primarily P mode type
Correct.
things. I thought, but they do see ones that penetrate deeper in too, is my
Yes.
recollection.
Yeah, you see a bunch kind of close to that dip.
They
But
tend
you
to be close
can't
to that dip.
Yes.
Okay.
But the ones here are just, I mean, I don't think they see them at all.
Okay, that's what I
And
was
also
wondering.
it's a more red giant than AGB star. So it's more closer to the top plot, right? The inertia contrast is not
okay.
as big as factor. I think AGB contrasts like a factor of 1,000 or something.
Yeah, it's a greater contrast for AGBs. Yeah, so you really maybe get the one at tip and maybe like a couple.
Right, okay,
Right.
good.
So red giant, you could see both P and G dominant.
See a few other questions. Yanshin, I think you had your hand up for.
Well, my question is actually, so what does this kind of calculation, which is really beautiful, how does that lead us? I'd like to get some more insights on how does this help us in understanding, for example, could this mode transport angular momentum inward to the core, in the sense that if you start from core and envelope differentially rotating, which is stellar evolution gives you for free. We know somehow the stars are communicating between the core and envelope in some longish timescale. Mm-hmm. Could the mode, for example, do anything in that communication? So be closer to your talk, is that any kind of insight we can draw from this kind of calculations?
Not directly from here, but it's definitely thought that torsional alphing. I think there's a work recently by what's his name? I can't quite remember. Japanese person. I'm terrible with this. Looking at the possibility of angular momentum transport by torsional alphing waves. And so I suppose indirectly this work connects in that if you can detect the presence of even just a weak field, I think that's extremely effective, according to their calculations. I mean, I heard there might have been some closure problems with the field configuration there, but they seem to kind of work for any kind of field, as long as you have field lines and extending from the, across the envelope into the core. But yeah, I mean, this work doesn't really deal with angular momentum transport in that sense.
Thanks.
If there are no other questions, I'll stop the recording, and we have scheduled after.
Could I just ask?
Oh, please, yeah, sorry.
I had my hand up, then I put it down because I thought that it was all covered by the last two questions, but as usual, I'll try and be a little going back. Could you go back to the diagram that showed before it hit the red giant phase and then it hit the red giant phase? This was, I think, the modes without magnetic fields yet included, but it showed a rather dramatic difference. I think this is what Norm was referring to and Yen Chin. Yeah, that's it. So as one moves from subgiant to RGB in some ordered sequence, so you have this great concentration. What is that dotted black line again?
Oh, it's the radius of the field that eventually gets added on.
Oh, okay. But the interesting question for me in this regard, and it affects all of the modes to be sure, is that there is this big entropy transport that's occurring as one moves into the red giant phase. And this is reflected in the eigenmodes. And it's really quite dramatic here in terms of the extent. So I wonder if you could just say a few more words about the process that's going on here. Norm referred to it as that mostly outside it becomes P mode dominance. But I'm not quite sure I fully understand what's G and what's P and why the modes look the way they are in terms of that internal concentration, and where the P modes that Norm's referring to, are they in this diagram?
I mean, so roughly speaking, the P mode cavity exists above the Lamb frequency. And the G mode cavity lies beneath it. So that this is mainly where the G modes.
What's the definition of a cavity in this regard?
So gravity waves can only propagate below the buoyancy frequency, whereas acoustic waves can only propagate above the Lamb frequency, roughly speaking.
Okay, so the discontinuity is it's reflecting this cavity.
Yeah, so the waves will kind of turn around when they get to their respective Lamb frequency, depending on the value of L.
So when a star passes from subgiant into red giant, there is a strong cavity structure that develops that wasn't there before.
The cavity structure was there in the main sequence, but they were much more separated in radius. So that means that you don't get mixed modes or don't get anywhere near as much mode mixing as you do in the evolved state.
And then this is also somewhat unrelated, or maybe it is. When people like Norm in his distant past do all of the interior modes for the sun, all of these magnetic splittings are all being included, and are they being observed?
No and no.
So basically this is a pretty wide open subject even for main sequence stars.
Well, I mean, I was really impressed by Cleo's talk.
Yeah.
But it also scared the hell out of me.
Well, yeah. May I just add one more comment on this? We believe it or not, we do these things in the early universe, but sometimes if you sum over the modes that are of low frequency, you can build up a kind of mean shape involving the nonlinearities that would give you a different solution. It's like a way to put in quadratic nonlinearities, for example, or even higher. Is that being used in these subjects now? Anything like that? Or is it all just linear perturbation theory off of a fixed background with no feedback?
I mean, I think it depends on the kind of star. I feel like there's some work done with Cepheid variables, which are much longer time scale, like lower frequency fluctuations, but I'm not familiar with that area at all. Certainly in stochastically excited or stars in which the oscillations are stochastically excited, it's all kind of linear. And that's what I'm mainly familiar with. I believe it's Cepheids.
Small.
Sorry?
And that's because the amplitudes are sufficiently small that you don't see that there is actually configurational change from low frequency modes.
So, I mean, in solar-like oscillators, so red giants, the amplitudes are very small and you wouldn't expect much nonlinear coupling, if at all. But it's not the case for Cepheid variables, which are, there's a much larger amplitude, lower frequency, kind of global instability excited oscillations. And I unfortunately don't know too much about those.
Yeah, well, you can see that I'm just trying to get a snapshot of the full state of the art in the subject, which I haven't been into for a little while.
There are lots of calculation of nonlinear mode couplings, different context. For example, Cepheid, like Cleo was mentioning. I did that for white dwarf in my PhD, and then with like Nevin Bamber did it for neutron stars, all kind of contexts where we do nonlinear, when nonlinearity is important. but we do it in the perturbation sense.
Yeah. Anyway, echoing Norm, I really enjoyed this. Great work.
Thank you.
I'll go ahead and stop the recording. Anyone who wants to stick around we have a half hour of chat scheduled.